Hi everyone, this is Carolyn Schechter, and today I'm going to be taking you through a derivation of the Michaelis-Menten equation. So I typed up most of the derivation, and then I'll be walking through each step. On the left-hand side of the page here, we have some starting equations. Km is equal to k negative 1 plus k2 divided by k1. Hold on, I just noticed a little mistake there. Okay, we have Vmax is equal to K2 times the total enzyme concentration, and then the total enzyme concentration is equal to unbounded enzyme plus enzyme that is bounded to substrate, or the enzyme-substrate complex. And we also have our actual chemical equations written here, just kind of showing you where we're getting some of these numbers from. K1 is for the forward reaction to enzyme-substrate complex. K negative 1 is for the breaking down of enzyme substrate complex back into unbounded enzyme and substrate. And then K2 is from the enzyme substrate complex becoming product and then unbounded enzyme again. So to start, our starting equation was the instantaneous rate of enzyme substrate concentration over time is equal to K1 times unbounded enzyme concentration times substrate concentration minus K negative 1 times the enzyme substrate complex concentration minus K2 times the enzyme substrate complex concentration is equal to 0. Now, using one of our equations on the left side here, we want to get the unbounded enzyme concentration in terms of the total enzyme concentration. So using that equation, we see that unbounded enzyme concentration is equal to total enzyme concentration minus the concentration of the enzyme substrate complex. So plugging in that E term into this first equation, we now have the instantaneous rate of enzyme substrate complex over time is equal to K1 times the total enzyme concentration minus enzyme substrate concentration times substrate concentration minus K negative 1 times the enzyme substrate complex concentration minus K2 times the enzyme substrate complex concentration is equal to 0. Now we want to factor this K1 term and this S term through this term here. So now we have K1 times the total enzyme concentration times substrate concentration minus K1 times the enzyme substrate complex concentration times the substrate concentration minus K negative 1. I'm sorry about that. K negative 1 times the enzyme substrate concentration minus K2 times the enzyme substrate complex concentration is equal to 0. So now we're going to move any term with this enzyme substrate complex concentration over to this side of the equation and factor out that enzyme substrate complex. So as you can see here, what we have is the enzyme substrate complex concentration times this whole factor, which is K1 times the substrate concentration plus K negative 1 plus K2 is equal to K1 times the total enzyme concentration times the substrate concentration. So now we just want to get the enzyme substrate complex concentration onto one side by itself. So we're going to divide this term here by this term. So what we have is K1 times the total enzyme concentration times the substrate concentration divided by K1 times S plus K negative 1 plus K2. Now what we're going to do is multiply the top and bottom by 1 over K1. So what we have now is the enzyme substrate complex concentration is equal to the total enzyme concentration times substrate concentration divided by substrate concentration plus K negative 1 plus K2 divided by K1. To make that look a little bit easier, our bottom term is actually going to look like this: the concentration of S plus K negative 1 plus K2 over K1. Now, as we can see, this term right here is equal to Km, which is our Michaelis constant, which is different for every enzyme. So now, plugging Km here, we have this equation right here. Enzyme substrate concentration is equal to the total enzyme concentration times the substrate concentration divided by the substrate concentration plus Km. So now that we have an equation for the creation of the enzyme substrate complex, we want one for the creation of product. So the instantaneous rate of change for the product over time, which is also just saying the rate, which is velocity, is equal to K2 times the enzyme substrate concentration. So now that we have this equation for the enzyme substrate concentration, we plug that in. So we have the rate is equal to K2 times the total enzyme concentration times substrate concentration divided by our substrate concentration plus Km. So now we have this last equation here, which is V max is equal to K2 times the total enzyme concentration, which is a term that we have right here. So plugging that in, we get V is equal to V max times the substrate concentration divided by the substrate concentration plus Km. Now, why can we say that K2 times the total enzyme concentration is equal to V max? Essentially what K2 is what is called the turnover number, and that's the maximum number of substrate molecules that an enzyme can convert into product for a catalytic site per unit of time. What that's really saying is the number of substrate molecules an enzyme can work with per second. And then since we're multiplying that by the total enzyme concentration, that'll give us the maximum velocity of this reaction. So now that we have Vmax plugged in here, let's talk a little bit more about Km. Let's say that Km was equal to the substrate concentration. When we plug that in, we now have Vmax over S divided by 2S, which is the same thing as Vmax over 2. So Km is really the substrate concentration when velocity is equal to half the maximum velocity. So now what we have right here is our Michaelis-Menten equation. I hope this was helpful, and please let me know if you have any questions or comments.